Whenever we look up at the night sky, we kind of just naturally assume the universe has infinite computational power, right? We figure the cosmos has this endless, bottomless memory to track every single atom, every stray photon, perfectly, down to the absolute deepest decimal point. But what if it actually doesn't? What if the universe, literally just like the hard drive sitting in your laptop right now, has a strict, finite memory limit? What if occasionally the universe just has to clear its cache?
Well, let's dive right into this. Welcome to this explainer on a genuinely fascinating new theoretical paper by Royce Boesnine. It's called Tension Theory version zero point 0.1, and it proposes a radically different idea that reality isn't built on infinitely precise, continuous math at all. Instead, it's an executable system. Today, we're going to completely break down how this model builds reality from the absolute bottom up. Here is a quick roadmap for our explainer today. We'll start with the flaws in modern physics, move on to tension as a primitive, look at the rules of a finite universe, see how space and time actually emerge, and finally, look at predicting an executable reality. Okay, starting with part 1, the flaws in modern physics and why our current mathematical models might actually be buggy. To really understand the solution here, we first have to take a hard look at the foundational assumptions of our current physics models. Right now, standard physics relies heavily on continuous spacetime, it uses global wave functions and quantum mechanics, and it pretty much just assumes infinite precision everywhere. But tension theory flips the script. It suggests a reality that acts much, much more like an actual computer. We're talking discrete updates, strictly local states, and hard, finite memory limits. The core of the issue is captured perfectly by this idea from the paper. Any system capable of evolving must store state, update it, and discard alternatives. And here's the kicker. These operations are not free. Current physics completely ignores the irreducible memory cost of existence. It just assumes that as reality updates from 1 millisecond to the next, processing that change costs literally zero energy or memory. But tension theory argues that zero-cost change, it's just impossible. Moving right along to section 2, tension, a fundamental primitive, the building blocks of a finite reality. So if we drop all that infinite math of the past, where do we begin? We start with the absolute foundation, a node. A node is a locus of state. You can kind of think of it as a tiny, completely isolated, single-pixel computer. It only stores a local state, and it is entirely bounded by its finite memory limit. A node has absolutely no idea what the rest of the universe is doing. It only possesses its own local, highly limited information. Next up, we have an edge. An edge is simply a relation between two of these nodes. Think of it like a network cable connecting two of those isolated computers together. It defines how they might interact or exchange information. But, and this is a really crucial point to keep in mind, these connections are not physical distance yet. We aren't talking about empty space or geometry here at all. This is just pure relational structure, essentially just showing who is allowed to talk to whom. And now we introduce the absolute star of the show, tension. Tension is a measure of the constrained informational difference between connected states. Basically, think of it as the fundamental pressure for change. When two connected nodes have a discrepancy in their information, tension builds up along the edge between them. And this tension acts as the primary driver of the entire universe, pushing the system to update and resolve that difference. Which brings us to section 3, rules of a finite universe, and how reality actually computes and updates itself. Okay, so now that we have our nodes, our edges, and our tension, how does reality actually do the math? Well, the universe, according to this paper, operates on a highly structured, discrete sequence called the update cycle. It is incredibly similar to how a computer processor ticks. Step 1, a node reads its local state. Step 2, it evaluates the tension gradients around it to see where the pressure is the highest. Step 3, it decides on a candidate update. Step 4, it applies that new state, which, critically, overwrites its memory. And finally, step 5, it propagates those new tension changes out to its neighbors. Literally, everything in existence is governed by this cycle. Now, because the universe is relying on this cycle, we get some very strict simulation constraints. There is finite memory per node, for sure, and a non-zero cost for every single update. Plus, there are no global reads or writes. Everything is strictly local. But the absolute most vital constraint is this. Overwriting older information means perfect reversibility is fundamentally impossible. Because memory is limited, when a node updates, the old data is erased, gone. The universe simply does not have a Control-Z undo button. So what does this all lead to? Let's look at Section 4, How Space and Time Emerge, the ultimate consequences of local updates.
This is the part where the theory gets truly mind-bending. The things we consider to be foundational to our reality, like time itself, are actually just side effects. Under tension theory, time is not some background cosmic clock ticking away independently. Time simply emerges because memory is finite. Because state updates overwrite old data, the system can only ever move forward. That one-way sequence of irreversible state transitions, that is exactly what we experience as time. Time is literally just the memory of change.
All right, so what about space then? Space is just a stable relational graph. It isn't a giant empty box that the universe sits inside. Instead, when a cluster of nodes maintains stable edges with bounded tension, they form a structured neighborhood. It's exactly like a social network. Distance isn't physical miles. It's just how many friend connections away you are from someone else. What we perceive every day as three-dimensional space is actually just an emergent mapping of these stable localized node relationships. If space and time are just emergent behaviors, what is a physical object? Well, a particle is simply a stable tension loop. Particles are not tiny, fixed spheres of physical substance. Actually, scratch the idea of billiard balls completely. Think of them more like whirlpools in a river. They are forms maintained purely by the balance of circulating pressure, keeping their shape tick after tick after tick of the update cycle.
And this brings us right to probability, which the paper beautifully defines as incomplete local knowledge. You know how in quantum mechanics we often talk about intrinsic randomness? Well, this model clarifies that apparent randomness is just an illusion. It's exactly like the fog of war in a strategy video game. A local node, like us, the observer, simply does not have the memory capacity to load the full map. We just can't see the whole board, so the universe looks probabilistic to us.
Which leads us to our final section, Part 5, Predicting an Executable Reality, what this model means for the future of physics. So what does this all mean? Does this model actually map to our known world? Or is it just a really neat thought experiment? It turns out, tension theory brilliantly explains the mechanisms behind our most trusted laws of physics without needing any of that infinite math. Quantum mechanics weirdness? Explained simply as unresolved local tension and graph history. The curvature of space-time and relativity? That maps perfectly to non-uniform tension distributions restricting how updates propagate. And information theory is no longer just a human concept layered on top of physics. In this model, it is the literal substrate of reality itself. And importantly, this isn't just late-night philosophy. The author outlines testable predictions where our traditional continuous models will eventually fail. This framework predicts a breakdown of continuum models at extremely small scales. It predicts hard limits on microscopic reversibility. It even predicts that the sheer physical cost of observation will redistribute tension, putting actual bounds on precision. This is falsifiable science, predicting exactly where the illusion of a continuous universe will finally crack. I absolutely love how this is summarized in the paper. The crucial point is captured perfectly in this profound quote. Computation is not an abstraction imposed on physics. It is what physics is doing. This is a complete paradigm shift. The universe isn't a magical geometric shape or an infinite wave function. It is a simulation, executing relentlessly, constrained by locality, tension, and the strict, unforgiving limits of memory. And that leaves us with a rather profound, lingering thought to close out on today. If reality truly is an executable system with a finite memory capacity governed by localized tension updates, what happens to the simulation when it finally runs out of space? I highly encourage you to read Roybos 9's full paper to explore these ideas even deeper. Thanks for joining me on this explainer, and keep questioning the limits of your reality.